Welcome! Today's video is about minimal clones. We fix a base set B. Last time we have seen that there is a largest clone over the set B, namely the set of all operations on B, and a smallest clone over the set B, which is the clone that just contains the projections. The clone of projections can also be described as a polymorphism clone. It is the set of all polymorphisms of the set of all relations over the set B. These are infinitely many relations. However, there is also a finite set of relations that has this property, and I will show you one such finite set of relations for which this is particularly easy to see. First, we add for each element of B the singleton unary relation that just contains this element. Note that this forces all polymorphisms to be idempotent. So all unary polymorphisms must be the identity. To eliminate all higher array non-projections, it suffices to add one more relation of arity 4, which I call PB4. It contains all four tuples A, B, C, D, such that A equals B or C equals D. To understand this relation, let's have a look at what it means that a binary operation does not preserve PB4. It means that there are two four tuples, A1, B1, C1, D1, and A2, B2, C2, D2 in PB4, such that the tuple A, B, C, D that we obtain by applying F component-wise satisfies that A is different from B and C is different from D. I have drawn such an example on the left. In this example, we have the red inequalities, and I don't care how F looks like elsewhere. What does it mean that a binary idempotent operation preserves PB4? It means that we should not see the situation on the left, no matter how we choose the four tuples A1 up to D1 and A2 up to D2. And it is now easy to see that this means that F must be a projection. I usually draw projections as on the right. Points in the image that lie on a line indicate that the function value of F must be constant along this line. So the two pictures on the right indicate the two binary projections. And this argument can be generalized to any arity, not just binary functions. This shows that for a finite set B, the projection clone is the polymorphism clone of a structure with finitely many relations. It is easy to come up with a proof of the same statement that also works for infinite sets B. A clone C is minimal if C is not the projection clone and C has no proper subclones, except for the projection clone. So we can draw this in the lattice of clones over the set B as the clones that are right above the projection clone on B. Every clone over a finite set B that is different from the projection clone contains a minimal clone. This is a consequence of Zorn's lemma that we prove now. Let B1 up to Bn be an enumeration of the elements of B. We will show that every descending chain of clones that are strictly larger than the projection clone has a lower bound, which is also strictly larger than the projection clone. The statement then follows from Zorn's lemma. So let C1, C2, and so on be such a chain. We consider the union, R, of all the invariant relations of all the clones Ci. Then we note that if we have a relation that is primitively positively definable from the relations in R, then this relation is already in R. The reason is that every primitive positive definition can only involve finitely many relations from R. So these relations are already contained in inf of Ci for some I. And inf of Ci is closed under PP definitions, as we already know from the previous video. The next observation is that R cannot contain all the relations, PB4, singleton B1, singleton Bn. Because in this case, for some I, the clone Ci would be equal to the projection clone, in contradiction to our assumptions on the clones Ci. So the polymorphisms of R form a clone which provides a lower bound for all the CIs, which is strictly larger than the projection clone. This concludes the proof. To understand such general proofs, it can help a lot to explore a bit the scope of the statement. Do we really need the assumption that the base set B is finite? It turns out that yes, this is needed. I will illustrate this with a clone C, whose base set is the set of natural numbers, and which is generated by the operation x maps to x plus 1. All operations of C only depend on one of the arguments, and the unary operations are precisely the operations of the form x maps to x plus c for some natural number c. If c is larger than 0, then the operation x maps to x plus c generates x maps to x plus 2c, but not vice versa. So this is a clone which does not contain a minimal clone. My question to the audience is, where precisely did I use the assumption in the proof? Be careful with the answer. Probably this is a good question to keep in mind when you look at the proof in the script. An operation f is called minimal if it is not a projection and if it is of minimal arity with the property that every operation generated by f is either a projection or generates back f. This is really just another formulation of the same idea. It follows straightforwardly from the definitions that every minimal f generates a minimal clone, and conversely, every minimal clone contains a minimal operation. So if this is not entirely clear to you, sit down and do the easy exercise. Now, Ivo Rosenberg's 5 types theorem provides a classification of minimal operations. Actually, it's not quite a classification, because in some of the cases we gain very little understanding about the minimal clone, so I rather call it a pre-classification. Rosenberg's theorem states that every minimal operation is of one of the following 5 types. First case, f is unary and f of x equals f of x for all x, or f is a permutation of prime order. Second case, f is binary and idempotent. Third case, f is a majority operation. Fourth case, f is a minority operation. So these are cases that we know very well from previous videos. Last case, 5, f is an idempotent k-ary semi-projection of arity at least 3. A semi-projection, we have to define. A semi-projection is an operation such that there exists an index I, such that if some of the arguments of the operation are equal, the operation returns the ith argument. So it equals the ith projection. If all arguments are distinct, there is no restriction on f. There are many nice things about Rosenberg's theorem. The first is that it has a very natural proof that's very easy to remember. The second is that it's useful if you want to verify that a given structure has no polymorphisms except for the projections. What you do, you verify for each of the 5 Rosenberg types, one by one, that there are no polymorphisms of that type. Then Rosenberg's theorem implies that the polymorphism clone of the given structure is the projection clone. There's another application that we will see next time. We can use it to prove the CSP dichotomy for 2-element structures. Each CSP for a 2-element structure is either in P or NP complete. And this is known as Schaefer's theorem, and it follows relatively easily from Rosenberg's theorem. After all this publicity, I hope that you are now sufficiently motivated for the proof of Rosenberg's theorem. In the proof of Rosenberg's theorem, we treat minimal operations arity by arity. In the unary case, we will have a look at some examples. Unary functions can be nicely visualized by drawing the domain elements as points and drawing an arc from A to B if f of A equals B. The resulting digraphs have the property that they consist of disjoint unions of loops and cycles, possibly with some root-oriented trees attached to the cycles. If we compose f with itself, this amounts to taking two steps in this digraph. In my first example, if we compose f with itself, we will get back f. So f is clearly a minimal operation and covered by Rosenberg's first type. In my second example, we see a three-cyclic permutation, which is also minimal, since, for example, f composed with f can generate back f. I should also show you some unary operations that are not minimal. Cyclic permutations whose order is not prime are not minimal. For example, if f is a four-cyclic permutation, then f composed with f is a permutation which consists of two cycles, and such a permutation cannot generate a four-cyclic permutation. We have another example with a three-cycle with an additional incoming edge. Here we have to look at the third power of f to obtain a function that is not a projection but cannot generate f. So again, f is not minimal. I think these examples should give you enough of the ideas to finish the proof. If f is binary, then the statement is immediate. Consider the operation head f, which is the unary operation obtained from f by identifying all arguments. If head f is not the identity, then we have a contradiction to the minimality of f, because the clone generated by head f must contain a minimal operation, which is again unary. So we could have chosen this operation instead of f, contradicting the minimal arity requirement for f. So f of x equals x for all x, which is the definition of what it means to be idempotent. If f is ternary, then all functions obtained by identifying two of the arguments must be projections. We now distinguish 8 cases according to whether we obtain the first or the second projection for each of the 3 binary operations. For instance, if we get 3 times the first projection, indicated by x, we obtain a majority operation. If we get 3 times the second projection, indicated by y, we obtain a minority operation. In 3 of the cases, f is a semi-projection, and in the remaining 3 cases, we obtain a Maltsev operation. If f is minimal and a Maltsev operation, it generates a minority operation. To see this, we consider again the operation f of x, y, x. If the result is the second projection, then f is a minority, and we are done. Otherwise, f of x, y, x equals x. And we consider the ternary operation g obtained by replacing the second argument y of f by f of x, y, z. It is straightforward to verify that g is a majority operation. But majority operations can only generate majority operations, and a function cannot be a majority and a minority operation at the same time, unless the domain has just one element, in which case Rosenberg's theorem is trivial. If f has arity at least 4, then we have to prove that f is a semi-projection. And this is precisely the content of a famous lemma. It's a real pain to write down the proof of this lemma. However, the idea is not complicated. It's the presentation that's tricky. If you sit down and write down the proof, you get lost in notation. So many authors distinguish many cases, but all of them are very similar and easy. So if you find a simple proof of the lemma, you should always test it, whether it also works for ternary functions. If it does, there's something wrong. Because we know there are some ternary functions that are not semi-projections. They might be minority or majority operations, but not semi-projections. And there's another challenge. You might have guessed it already. We have to pronounce the name of the lemma, of the author.
Swierczkowski. Swierczkowski.
That was not bad.
Swierczkowski.
The final case is that f is an operation of arity at least 4. Then our assumptions imply that f is what I call a weak semi-projection. For any two distinct indices I and j, there is an index s which depends on I and j, such that if the ith and the jth argument of f are the same, then f returns argument at position s. The lemma of
Swierczkowski
says that in this case f must already be a semi-projection. In other words, the function Sij is constant. First of all, clearly if Sij equals I, then it's the same as saying that Sij equals j, because xi and xj are anyway equal. So we introduce some special notation for weak semi-projections that will make the proof more transparent. For some subset S of indices of size at least 2, we define E of S as follows. Consider f applied to some arguments, the same value for all indices that are in S. Suppose that the weak semi-projection f returns xi. If I is in S, then E of S is defined to be S. Otherwise, E of S is the singleton set that just contains I. Note that E is monotone. That is, if S is a subset of T, then E of S is a subset of E of T. We need to show that there exists an index I that is contained in E of S for every set of indices of size at least 2. Because then F must be a semi-projection. The statement is clear if the domain has only one element. We first prove the following claim. We prove that there exists a 2-element set of indices, S, such that E of S equals the singleton set I. To prove the claim, we consider the set 1, 2 and the set 3, 4. If E applied to one of these two sets is a singleton set, we are done. Otherwise, E of 1, 2 equals 1, 2 and E of 3, 4 equals 3, 4. But this is impossible, because then the function f, where we equate the first two arguments, and the third and the fourth argument, must be equal to x, and it must be equal to y, for all x and y, which is only possible if the domain has size 1. To prove the lemma, let T be a set of indices of size at least 2. It suffices to show that the index I from the claim is contained in T, because then F is the semi-projection that returns that ith argument whenever any two of its arguments are equal. We first consider the case that T does not contain I. Then E of T is contained in E of all indices except for I by the monotonicity of E. Now this set contains the set S of the claim, and E of S is the singleton set that just contains I. This shows that E of T equals the singleton set that just contains I. The next case is that T does contain I and is of size 2. Then the complement of T also has size at least 2. Here we use our assumption that the arity of F is at least 4. The same argument that we used in the proof of the claim shows that the intersection of E of T and of E of the complement of T must be non-empty. In fact, E of the complement equals singleton I, as we have just seen earlier. So we conclude that E of T equals T. Now, the same holds for all supersets of T by the monotonicity of E. And this concludes the proof. This concludes the proof of Rosenberg's theorem. As I already said, next time we'll use it to prove Schaefer's theorem, which is a dichotomy for the constraint satisfaction problem over two element structures. So, see you, take care, until soon.